hostage to the particular distribution of inputs you get. Right? So randomization is used to avoid the dependency and force a certain, averageness to your input. Right? So the point is that when you talk about randomized algorithm, we are not talking about, well, if the input is, nicely distributed and so on. But instead what you're going to do is you're going to force the input to follow the whatever distribution that's needed in order for you to get good average case performance. Right? So the key point which I'll emphasize again is you need to enforce a random distribution of data. Okay? And the third reason, third class algorithm we'll talk about are probabilistic algorithms, which means that they don't always produce, say, the most optimal solution, but they have a high probability of producing an optimal solution. Okay, so we'll talk about those three, but today we are going to continue with the discussion about decentralization. Okay? So you might recall where we left off, which is at this point where we said, well, here is a protocol for media access. So everybody tries to grab the network, and you want to make sure that if multiple people grab the network and start transmitting, then it's all wasted, and because nobody gets through. And if nobody grabs the channel, again, the channel is wasted. Right? So then we said, okay, what's the way to develop a randomized algorithm where each host with a probability p tries to transmit, okay, tries to get hold of the matrix of the slot. And we formulated that, and we said, okay, the probability p should be 1 by n, right? So we said with the if you set your probability of transmission to be 1 by n, then you maximize the throughput, and we then derive what is the maximum throughput, or at least more specifically what we said is, okay, what is the fraction of slots that will be gainfully utilized, right? So you don't have slots going waste because multiple people, use the slot and then they clobbered each other's transmissions, or nobody tried and therefore, there's nothing transmitted, okay? So what we said was approximately 1 by e transmissions, 1 by e slots was utilized, and e minus 1 by e slots go waste. Okay, so well, that's like 2/3 going waste. Okay, anyway, so we will. It's not by itself. It's not a great protocol, and somehow one needs to make it better. But let's continue our analysis. Okay, so and ask the question: how long does it take for a single host to get to transmit? Right. So let's again do some basic probability calculations, right? The probability that it fails the first time is very high, right? Because the probability it succeeds is only 1 by ne, right? And so the probability that it fails is 1 minus of that. So it is 1 minus 1 by ne, okay? So now, what is the probability it fails k times? So you just have to raise it to the power k. Right? So the probability of failing once is 1 minus 1 by ne. So you raise it to the exponent k. You say how long, what is the probability of it failing k successive times? Okay? So now, once again, we have this identity that 1 minus 1 by x power x goes to e as x goes to infinity. Right? So we can apply that here. And so we see that if k goes to the value of ne, then this probability goes to somewhat small value, like 1 by e, right? So we said 1 by, again, remember the identity. Right? So we just apply that, and then we say, okay, if you try any times, well, then you have a probability of transmitting, which is 1 by E. Okay? Now, that's not a high probability, right? 1 by E is like 1/3, right? So it's not a very high probability. And okay, I'm sorry. So this is the failure probability, right? So when you say the failure probability is 1/3, that means there is a reasonable chance of succeeding, but the failure probability is still large enough that you can't say, well, I'm almost certain that it would have been able to transmit. Okay? So then you can ask, how many more attempts do you have to, how many more slots do you have to wait before you can say, this entity would have transmitted. Then let's try, instead of saying k equal to NE, let's try k equal to NE times ln n. Okay? Or NE times C times ln n. And then we can try to work out this quantity. And once again, 1 minus 1 by NE equal to the power NE. The underlying quantity is nothing but 1 by E, right? So that becomes 1 by E raised to the power C ln n. And we know that E raised to the power ln n is nothing but n, right? That's the definition of logarithm, right? So you take the base, raise it to the power log of something, then that something is the result. Okay? So this ends up being basically n to the power minus C, because ln n becomes e to the power ln n becomes n, and so we have a minus exponent there and become n to the power minus C. Yeah?
In this we are assuming that when x tends to infinity, then this is the problem. We are assuming that it will take infinite.
No, we are not taking that. It is an approximation, right? So what I'm saying is that it's approximately that for even modest values of x. So if you take x equal to 10, it'll already be pretty close. Okay, it'll be like 10% off or 5% off from E. So what this means is that if the host tries order of n times, it has a reasonable chance of success. Like what we calculated was approximately 2/3 chance of success if it tries order of n times. But if it tries order of n ln n times, then the probability is very high, right? Because the failure probability has become like 1 by n to the power c, right? So if n is reasonably large, then n to the power c is extremely, is very large. And so the probability of failure becomes very, very small, right? So you can say virtually certain that in n ln n attempts, it'll get to be able to transmit. Okay? So again, so we are trying to answer the question how long before a host can expect to transmit, and what you are saying in order of n, there's a reasonable chance. If you give it, if you really want to be sure, then give it n ln n times. Okay? So now what is the expected wait time? Okay? Remember recall the term expected and average, right? So in probability we use the term expected, whereas in less formal, the less formal term will be average, right? So we want to say what is the average time a host expects, because we are saying that in a sense the worst case is like n ln n, right? And so then the question is, what is the average? So the average is given by what is called the expectation, okay? And the notation, that's a notation for expectation of a random variable x. And this is sort of a general identity, right? What it says is that if the value is going to be j with a probability of something, right? Then you basically take the weighted sum of, whatever probability for which it is going to have value 0, whatever probability for which it's going to have value 1, value 2, and so on, and you multiply, you take the weighted sum, and then that's going to be your expectation. Okay? So let's expand this sigma on the right. So what that says is that if j equal to 1, then the probability of succeeding is, so now we use p to refer to the probability with which this thing is going to succeed, right? So we are not so the probability p here simply stands for the probability that the wait time is that a given host is going to succeed when it transmits. Okay? So if it doesn't get to succeed, doesn't get to transmit the first time, then what should have happened is that it failed the first time and succeeded the next time, right? The failure probability is 1 minus p, and then the success probability for the second time is p, right? So that's why you get the product of 1 minus p times p, and now you have waited 2 slots, so it has to be multiplied by 2. And then again, if you get to transmit in the third slot, that means you failed the first 2 times, so 1 minus p squared is the probability, and the third time you succeeded, that's the probability p, so you get 3 times p, 1 minus p squared times p, and so on. So that's your, now if you can factor out p, right, and then you get the sum, which is of the form I times 1 minus p to the power I minus 1, right? So how do we do this? So how do we do this? We want to sum this series, right? I times x to the power I minus 1. How would we compute the sum of this? Any idea? So the form ix power I minus 1 looks like the derivative of x power I, right? So that gives us an idea. Maybe we can do some tricks involving calculus, and maybe we'll succeed. Okay, so we start from a known identity involving the sum of x power I. Okay, and you know 1 by 1 minus x equals x to the power sum of x power I for I going from 1 to infinity. Okay, so this is a known identity, and if you don't know it, you can look it up. Okay, so now let's differentiate both sides. So you'll get on the left hand side, you'll get ix, sum of ix power I minus 1, right? So you're just differentiating the x power I over here. So you'll get ix power I minus 1. So you get this on the left hand side. Now if you differentiate the right hand side, that's nothing but 1 by 1 minus x whole squared. Right? So now you have a compact sum for this quantity. This series now has a compact sum. Okay. Now what you can do is you can now substitute the value of x. In this case, x was 1 minus p. Correct? So if this summation I times 1 minus p power I minus 1 is of the form I times x power I minus 1, that means x is 1 minus p. So if you substitute x equal to 1 minus p, then 1 minus x will become p, right? So this just becomes 1 by p squared, or minus 1 by p squared. I don't remember what the sign is, but it becomes 1 by p squared. And so, and then remember there is already a p outside, right? So that we factored out. So p divided by p squared is going to be 1 by p. So that tells us the expected wait time is 1 by p. Okay? And once again, well, we went through what appears to be somewhat detailed analysis, but we get a very intuitive results, right? So if probability of transmitting is p, then the expected time for you to transmit will be 1 by p, right? This is a very familiar result, very intuitive result, and it's reassuring that you get that intuitive result. Okay, so so let's ask the next question. Okay, so now we said what is the expected time, right? And then we want to ask again, how long will it be before every host would have a high probability of succeeding? Okay, so now we have said, okay, on the average, you wait for 1 by p time, right? So on the average, the wait time is 1 by p. Now, you want some sort of fairness, right? You want to say, okay, everybody eventually gets to transmit, right? So if you design a protocol, you want some sort of fairness. And so you want to study if this protocol is fair and whether everybody will eventually get to transmit. Okay, and then you want to, the way you estimate that is by saying, okay, how long before, what is the expected time before almost everybody gets to transmit? Okay, and so if we what we computed so far is the probability that one of them will succeed. Okay, so let's use the notation S of I comma k, right, to denote the probability that host I succeeds in k steps, right? Within k steps, what is the probability that host I succeeds? Okay, so now if you want to say what is the probability that everybody succeeds, then you want to say that I want the host 1 to succeed, the host 2 to succeed, host 3 to succeed, all the hosts to succeed. Okay, so if you think of a host succeeding as an event, then you are asking for the probability of the union of these events to happen. Okay, so that's why we have Sk equals union of Sik. And if you want the probability of S of k, right? So remember that there's what is the probability of A union B? A is an event, B is an event. What is the probability of A union B? Right, so this is PRA plus PRB right? So if we add probability A and probability B, then we will be double counting those instances where A and B both occur, right? So because A and B both occurred, that will be counted under A and that will be counted under here, right? So in order to get the right value, we need to add that and subtract the intersection so that the intersection things show up only once, right? So this is something that we know, and when we derive bounds, right? Many times we are not interested in exact values, so we might say, I just want a bound, and then you could say that, right? So you know that this right hand side is less than so even though the equality doesn't hold here, you can say the left hand side is less than or equal to the right hand side. Okay, and so this will give you a way to at least get an upper bound, because summing these probabilities is easy. Reasoning about when these things could occur together or and so on can be more difficult, right? Thinking about all possible combinations. Okay, 3 of them would have succeeded, and the rest of them haven't, or 6 of them have succeeded, and then you need to worry about which 6 have succeeded. So all of those combinations, reasoning about them, can get complicated, and then so you might say, well, I'm not going to worry about those details if I'm only interested in giving sort of a rough upper bound. Okay, so we can use this to estimate how long it takes, and we can say, okay, let's say I put k equal to ne, right, and then I simply substitute in this formula. Okay, and then you get this value, because again, remember, PR of S of I comma k when k equal to ne, right? So when k equal to ne, that value is 1 by e, right? So this is what we derived a while ago. The probability that a single process or single host would succeed within any trials is 1 by e. Okay, so this is what we calculated a while ago. So you take the sigma for over n, so it just becomes n times. So 1 by e added n times, so you get n by e. Okay, which makes no sense, right? As a probability, n by e is generally larger than 1, right? So what does it tell you? Anybody?
That they're still failing. That there's still a lot of them that are failing.
No. that's true, but what it also says is that our bound is really loose, right? And it's kind of, you think probably this bound is meaningless because it's giving you a value that's could be arbitrarily larger than 1. So it's probably not very meaningful. Okay, so we can see that this union bound is not giving us useful results when you set k equal to any. Okay, because when k equal to any, there is so much intersection, events happening, and when we ignore them, we get grossly overestimate. But suppose we set k equal to Cn ln n. Okay, so then we know that this probability becomes n to the power minus c type of thing, or if you work through the details, it will actually be n to the power minus c by e. Okay, it doesn't matter, but this basically the point here is that because you have a geometric series, it's going to converge into something relatively small, and in this case it's going to be, if you go through the summation, it will be n to the power e minus c by e. And so if you set c equal to 2e, right, then this becomes minus 1, right, n to the power minus 1. Right? If this is 2e, then 2e by, if this is 2e, then this becomes e minus 2e, that is minus e by e is minus 1, right? So this will become n to the power minus 1, which is relatively small, right? So 1/n of a chance, when you're talking about n quantities, they can say is small enough, and I'm willing to accept that. So what it tells you is that by the time you set k to Cn ln n, your bound is useful because it is relatively small, right? And then you know that at this point it is useful, and so you can conclude that by the time you get to Cn ln attempts, everybody would have had a chance to transmit. Okay, so you can say that with the probability of n minus 1 by n, I can say everybody has transmitted. Right? That's very close to 1. Okay, so what can we say? So we were talking about, yeah.
So 1 by n is n to close to 0.
Correct.
It won't be near to 1. And here
No, I said n minus 1 by n will be close to 1. Okay, so I said, so the probability that not all of them have succeeded is 1 by n, which is the same thing as saying that with the probability n minus 1 by n, everybody would have succeeded. Okay. So yeah, so the point is that, while we have to sort of refresh our memory and work through the details, it's basically just high school probability stuff, and everything works from there. So although the protocol that we talked about so far is not particularly efficient, it is really the basis for all things are done on Ethernet and Wi-Fi. The only difference is that you don't start with some very low probability. Right? You start with essentially p equal to 1. So if you have something to transmit, you're going to go try to transmit. Okay, this way, if your assumption is that most of the hosts don't have things to transmit at any time, right? That's how you want your network to be, right? You want people to be able to transmit when they have data to transmit. So if that's how you engineer the system, then most likely when you want to transmit, the network is free. So you go and transmit. Okay, in that case, if the network is actually free, then immediately you get to use the slot. The slot doesn't go waste. But what could happen is that, there could be times when there is contention and multiple entities want to transmit, and then what these protocols do is they adjust the probability. Right? Essentially what happens is that each time there's a collision, the probability of transmitting is half. So the first time they try, if there's a collision, then everybody will try again with the probability half. Then there's a collision again, then they will try again with the probability 1/4 and so on. So obviously it's an exponential series, so even if a lot of entities are, even if n entities are trying to transmit at the beginning, in log n time, in log n rounds, only one of them will be trying to transmit, and so they will get to transmit. So during times of contention, you have only log n slots that are wasted before somebody gets to transmit. But under sort of benign conditions, the network is always available. You get to transmit as soon as you want. Okay, so let's look at the media access was sort of somewhere between an abstract and concrete problem. Okay, so now let's go to something that's a little bit more abstract, and we'll go through a couple of abstract problems before we start discussing randomization, randomized algorithms. Okay, so a common problem is called coupon collector. Right? So think, let's say you buy cereals, and you're told that there are 10 different coupons, and if you collect them all, then you can compete in a draw for prizes. Okay, so, well, obviously, this is a technique that cereal manufacturers use to sell more cereal, right? The children say, hey, I want to, get this prize, so I'm going to buy cereal, right? So they say there are 10 types. Let's say n equal to 10. There are 10 types. So you want to buy cereal boxes until you get all of the, 10 coupons, let's say. How many boxes do you think you have to buy before you get all 10? Guess. 100 boxes. Wow, you're so pessimistic. If this was the case, then the marketing program is a failure, right? So people will say, oh, 100, I'm not going to buy 100. So what? So someone looking at it might guess that it might be of the order of 10, right? Which, of course, is wrong, and it's also not of the order of 100. So the key problem is that, let's say you have acquired the intuition for why it takes time. You can sort of see by thinking about, let's say you have 9 coupons, and you are trying to collect the 10th coupon, right? So if you buy a new box of cereal, then the probability that it contains the coupon that you want is very small, right? It's only 1/10, right? So initially you can collect, right, the first 2 boxes, probably you'll get 2 distinct coupons, so you're doing well, right? And this is again what the manufacturers want, right? So you get encouraged, and then so you say, hey, I'm going to get all the coupons down quickly, and then it takes longer and longer, but you've already invested so much, right? Then you say, okay, yeah, I got 8 of them. How much longer is it going to take? So I will buy more. And well, they have a great marketing campaign, right? So yeah, this is what that says. That let xj be the number of attempts it takes for you to get the jth coupon, right? So that is 1 by pj, which is sort of again a standard thing we already went through, where pj is the probability of getting the next coupon. Okay, so we can go through the details. We can go through a careful derivation here, which is there on the slides, and you can go back and look at it more carefully. But what I want you to think about is the relationship between this problem and the media transmission problem that we just looked at. Okay? Because in the media transmission problem, we wanted to know how long does it take for everybody to transmit, right? And that is kind of similar to collecting all the coupons. And the reason why the time for one entity to transmit, right, one entity to have a high probability of transmitting differs from the time for everybody to transmit is because because after, again, let's say you've gone through, k of them have managed to transmit, right? The next slot might go to any one of the entities, right? But you're making progress only if it goes to an entity other than this k, right? So essentially what you're trying to say is that each time you flip a coin and determine who is going to transmit, right? everybody is equally likely to be the winner at that point. But you want only the people who you have seen before. You want them to win, right? This is the same thing as saying, I want, when I flip the coin, I could get any coupon here, but I want the coupon to be the one that I haven't seen so far. So it's exactly the same problem. And so the bound that we derive here is, sort of the right thing. So in order for you to have a high likelihood of collecting all the coupon, you need to have bought m log n boxes of cereal. Okay, so it's not n square, it's n log n, right? So right. So next sort of abstract problem. Okay, this is called the birthday paradox, right? So how many people should you have in a room before you have a high probability that two of them share the exact same birthday, right? Again, remember, I'm not saying, you're born on November 5th and he's born on December 5th. That's not the same birthday, right? You have to be both born on November 5th, right? So what is the how many people does it take before the probability of having two people with the exact same birthday is relatively high? Let's say more than half. Guess. Again, no wrong answer, that's just a guess. 25. Right. So people who already know the answer are not supposed to guess. Right? This is only for guessing. So that seems very surprising, right? But we can actually do a quick calculation that shows, in fact, this is correct. Okay? Okay, this is fine. So the probability that I plus, let's say you look at these people in sequence, right? And you have looked at I persons and the I plus 1 person you're looking at, right? You want to see, so what you want to do is the way you tackle this problem is to say, well, I don't know exactly how to calculate the probability that two people will have the same birthday. But what I can do is I can calculate the probability that none of the people have share a birthday, right? That their birthdays are all distinct, right? And then if I do 1 minus of that, that means more, there are some duplications, right? So all I want is that there be more than one person with the same birthday. So if I calculate the probability that the birthdays are all distinct and then do a 1 minus that, I get the value, right? So what I'm doing now is I'm trying to calculate the probability that the birthdays are all distinct. So I want to say, what is the probability that the I plus 1 person in this room, his birthday or her birthday is different from everyone else, right? So I birthdays are already taken, right? Because there are I people already in the room. I plus 1 person is coming in. So out of the n possibilities, because n should be 365 if you're talking about our normal years. And so I of those are taken out. So the probability that it's not a duplicate is the probability that I plus 1 birthday is one of the remaining days. So that's n minus I by n. Right? So now, once again we have this calculation. So the way to think about expected number of duplications is to say, well, if that is the probability, then with that probability, the ith person doesn't add any duplicate birthdays, right? But with the probability 1 minus pi, you're adding one duplicate birthday, right? So now, this way we can translate it into some sort of a quantity other than 0 or 1, and so we have a probability that we have some sort of an expectation of how many duplicate birthdays is added by the ith person, and then that simplifies, obviously 0 times pi is 0, so it's just 1 minus pi, and then we substitute pi equals that value. So if you substitute that and you simplify it, this becomes nothing but I by n. Okay? So now each person is adding that probability of or that many expected number of duplicates, right? So if you want to go through k persons, then you want to say, okay, what is the expected number of duplicates added by the first person, add that with the number of expected duplicates by second person, third person, fourth person, we just sum over this quantity. And so we sum over this I by n, and that's nothing but, you can take the 1 by n out, and the n is a constant here. And so that is our familiar summation of 1 to n. And so you get n again minus 1 by 2n. And so what does it take for this expected value to get to 1? You want the capital N to be of the order of small n squared, right? So when the capital N is of the order of small n squared, this whole quantity will become approximately 1, right? Or half. Okay, so when, so you can see that by the time you get the square root of the number of days in the year, your probability of duplicates is quite high. Okay, and so I guess square root of 365 is like, it's not square root, there's a 2n here, right? So, so the answer, if you calculate this, I think comes out to be 27, and the actual answer is, I think, 24.6, which, we are making certain approximations here, which if you don't make those approximations, then you will get the value to be about 25. Okay, so again, stepping back for a second. So coupon collector and birthday problems are actually two sides of the same problem, right? In the coupon collection, you are saying, I want every one of them, okay? And it says, okay, to get any one of them takes a short time, but to get every one of them, it takes much longer, okay? And the birthday problem says that I don't want any duplicates, right? So I want there to be no repetition, whereas in the previous case, we want everybody to be represented, right? So what it is showing is that if you want no duplicates, then the number that you can have is very small. If you want everybody there, the number is very large, okay? And again, if you take the birthday problem and ask for the coupon collector version of that, then that is, how many people do we want to have in a room if you want to ensure that, every day of the year is covered, okay? We are not saying there must be 2 people with every one of those birthdays. We are saying that every birthday is covered, right? So there is 1 person in the room, no matter what birthday you choose. And that is, again, if you do the calculation, it will be the coupon collector calculation. So you've got to go to more than 2,000 people, right? So what you see is that this factor of 100, right? If you want just 1 duplicate, then that's 25. That is, if you don't want any, repetition. Okay, what's the minimum? Then what's the maximum number of people you can have for no repetition? That's 25, and you need to go almost 100 times that if you say, I want everything to be represented. So duplicates, so those are the 2 sides of the problem, and let's go to a problem that's more general and more abstract, okay? And it's called balls and bins, okay? So the problem is that you have a number of bins, and you throw balls at random, okay? Because you're throwing them at random, some of them will end up in multiple may end up in the same bin or not. So we want to ask the question, okay, what's the chance that different things, what's the distribution of balls into these bins? Okay, so we could ask, okay, how many balls can I throw before there will be 1 bin that has 2 balls? Okay, so what is this problem? This is the birthday problem, right? So let's ask another question. If you want to make sure that every bin has a ball, what's that problem? That's a coupon collector problem, right? So that's why this is this is a more general problem. Now we'll see why it is more general, because I can also ask other questions. So what's the maximum number of balls in any bin? Right? So I could ask some sort of occupancy question. Right? I threw things at random. Now what is the occupancy? Right? And so it's a problem that arises if you, let's say, want to think about hash tables, right? Because you expect, you think of hashing as, computing some sort of a random function on some key and putting it in the bin given by the random function, right? And then you want to ask, okay, what is the collision, what is the expected collision, what is the worst case collision, and things like this. And what's this going to give you? It's going to give you collisions, yes, but what case of collisions? It's going to give you like a worst case, right? Because I'm asking you what is the maximum number, right? So suppose I look at all the hash table slots. I'm asking what's the maximum that I expect to see in any hash table slot, which is basically saying, okay, what's the maximum number of collisions I experience, right? While retrieving any one thing. Okay, so that's why we look at these abstract problems. And so these two calculations we have already done, right? So this calculation is also actually not that difficult, but I'm not going to do that here. You can look up these slides and you will see that it is actually not that complicated to do it. Okay, so we'll just summarize the results. So, so the first one is the birthday result, right? So if you are throwing n balls at random into n bins, then the number m for which at least one bin will have 2 balls is square root 2n. Okay, this is the value we derived from the birthday problem, right? You remember n into n minus 1 by 2n, right? So you do various square root stuff and you'll get this. Okay. Now, no bin is expected to be empty. Again, this is a coupon collector problem, so m is going to be n ln m, right? So you can see that to make sure that all slots are filled, right? Again, if you think about it in a hash table context, if you want to make sure that every hash table slot has something in there, if you want to get to the point, then the average number of elements in each hash table slot has to be ln m, right? So it just says that you want to really fill up the table before every hash table slot is going to be have some entity. And the expected number of empty bins is given by this. This is the formula you get from the calculation on the previous slide, which we didn't go through. And well, we don't quite understand that. So let's try to set m equal to n to simplify. Okay, because again, if you think about hash tables, generally speaking, you will have a hash table of size n if you expect to put order of n elements in there, right? So the size of the hash table should be of the same order as the number of elements that you want to put into it. Okay, so that's why the situation of interest is when m equal to n, and then you can go through the calculation of this, and then you will get that the maximum balls in any bin is of the order of ln n by ln n. Okay, so to get an idea, right? So ln n, let's say n equal to million, ln n is approximately 13 or 14. Okay, and ln n, which is ln of 14, is like 2.5 or something like that. So this quantity ends up being of the order of 6. Okay, so what it says is that if you have a hash table with a million entries, a million slots, and then you hash a million elements into this hash table, then there are going to be the maximum elements that you expect in any one thing is about 6. Okay, and this is sort of a probabilistic bound. It's not the absolute maximum, right? The absolute maximum is n, right? So there is a non-zero probability that every one of those randomly tossed balls ends up in the same bin, right? So that's not what we are interested in, because that's kind of uninteresting, right? It's such a low probability event you don't care. Now, obviously, that probability is much lower than, let's say, the universe exploding or folding on itself and so on, right? So we are not interested in that minuscule possibilities. So once again, let's say the probability of interest is 1 by n, right? So we want to say that in n minus 1 by n of the cases, okay, what will be the maximum occupancy, right? And that is what this gives you, right? It gives you that in n minus 1 out of n times, the maximum occupancy will be this value, okay? So it gives you a handle on, what the occupancy is going to be. So the point that I will make several times and repeat many times is that this bound is based on the assumption that balls are being thrown at random. In most of the cases when you actually work with real world data, the data is not random, right? The data is not necessarily your friend. So it could be skewed, it could be bad. So you can't say, oh, if the data is random, then I have a certain probability, and therefore I have a randomized algorithm that achieves a certain complexity. Okay? The definition of a randomized algorithm is one that forces randomness, okay? And it doesn't rely on the input itself being random, okay? So when we talk about hash tables, probably in the next lecture, we will talk about how you need to enforce or ensure this randomness in the function that you use for hashing. Okay, even if the input is not random, you need to ensure that somehow you're getting randomness. Okay, so now that we have done some analysis and looked at abstract problems, let's look at very quickly review some of the things we have done in the past. One of them is we discussed a version of randomized quicksort. And remember, randomized quicksort means you pick a pivot at random, right? So it's not going to be the first element or the last element or the middle element. It's going to be picked uniformly at random, right? So any one of those elements could be picked with equal probability. Okay, so that's the meaning of uniformly at random. Oh, what happened? Okay, so because you're picking it uniformly at random, the split could be any way, right? So it could be half-half, n by 2 minus 1, n by 2 plus 1, n by 2 minus 2, n by 2 plus 2. All of those splits are equally likely, and that's why you get to use this as the recurrence relation, where you have, this is the cost of sorting one side, one partition, this is the cost of sorting the second partition, and we are saying that the size of the partition can vary from I to n minus 1, and therefore each of them are equally likely, and so we put a 1 by n to say, okay, I'm going to take the average across n such possibilities, okay, and we have of course done the calculation, and the calculation turns out to be, the solution to this turns out to be n log n, right? And again, the point is that we quicksort, if you assume that the input is random, right, then you could choose any pivot and you'll get n log n time, right? But we can't assume things are at random, right? As we know that we could make that assumption, and then we might get some cases where things behave very badly, something that we looked at in the first midterm. So by forcing randomness, we can make sure that this bad thing doesn't happen and we get actually this n log n performance. So let's look at another simple algorithm. Again, we are talking about how to do a simple analysis, how to simplify algorithms, avoid sort of a lot of centralized decision making, bookkeeping and all of that. So in that spirit, we looked at quicksort. Again, we just choose a random. We are not trying to do a complicated analysis to figure out what is a good pivot to partition. We just choose something at random. Same way, we are going to look at a couple of more algorithms where by choosing things at random, we are able to avoid a complex analysis. Yes?
Okay, so here we have actually assumed that the input is random, right? Like if we are not considering those inputs which are, which gives, like, which are made explicitly to, like fail this, or it's not general, right?
No, it is general, right? We don't care about where the...
It depends on if the input is random, then it's like...
No, the whole point is that the input is not random. And still, you get this expected performance. That is, what it says is that if you run the algorithm many times, right? So I think the point you're making is that this does not guarantee that for a particular case, right, that you will get m log n time, right? It is still possible because each time you choose a random, it's going to split it in one way. It's not taking this average, right? Any one run is going to split in a certain way, right? So when we talk about randomized algorithm, so what we talk about is the expected runtime across many different runs of the same algorithm, right? It doesn't matter what the input is, right? You can, if you run it many times, let's simplify this. Let's say you are given one input, right? And you run the quicksort algorithm many times on the same input, right? Now what is your average performance? That will be n log n. Okay, that's one way to interpret that, right? A randomized algorithm doesn't give you a guarantee that the worst case, absolute worst case performance is going to be n log n. That's why we still use the term expected complexity. We are not saying the worst case complexity of a randomized quicksort, because the worst case complexity remains the same, n squared, right? But what we are saying is that regardless of, but in the case of non-randomized quicksort, like the one that we looked at in the in midterm 1, we said, okay, if the list is already sorted, then each time you give a sorted list to the quicksort algorithm, it's always going to take n squared time, right? Whereas by doing this in a randomized way, you know that across many different runs, you're going to achieve n log n. So a particular sort might still be n squared, but over many calls to the sort function, you're going to get n log n performance. Okay, and that doesn't depend upon the input. Good question. I should have pointed that out more carefully. So cache eviction is another problem, right? So you have caches, processor caches. You have a paging system, virtual memory page system, where you have a page fault and you need to decide what to throw out, right? So unfortunately, the optimal algorithm is one that knows about the future, okay? And a number of algorithm books, go through, consider this scheduling or cache eviction problem for talking about greedy algorithms, dynamic programming, and so on. I generally try to avoid that because it usually puts me off, because I don't know the future, and so why am I wasting my time, thinking about an algorithm that possibly could never make any sense. But the reason why it's talked about is because it gives you at least a reference point. It tells you what is the best that's achievable if you have an article to predict. But obviously in practice we can't predict, so we have to figure out something to do. So the problem is that because we can't predict, whatever heuristic we use to maybe guess what the future is can fall flat, right? Same thing like our quicksort case, right? So whatever heuristic we might use to pick the right pivot might fall on its face for certain choice of inputs. So suppose you want to say, I'm not going to be consistently bad. Okay, I may be bad one time, but over time I will not consistently make poor choices. And again, that's where randomization comes in, right? So you can say, well, I have some set of candidates that I could evict. If I choose a random number generator and pick it at random, at least I know that I won't always end up being very poor, right? So the idea behind randomized algorithms in many cases is that you will consistently not get into this worst case behavior, right? You'll get into worst case behavior once in a while, but on the average, you'll be okay. So finally, we are going to talk about the more involved set of algorithms, okay? The one where we are so you remember the closest pair algorithm that we discussed way back when we were discussing, which chapter was it? Divide and conquer, right? So it was a pretty complicated, involved algorithm, right? So we had to say, oh, imagine the square, there could be only so many within that square, and you need to compute all of those that could be within this thin strip, and in order to compute these things within the thin strip fast, I need to keep the point sorted along x direction, I needed to keep it sorted along y direction, and so on, and so the algorithm was quite complex, right? So what that, generally speaking, when you have a complex algorithm, that usually means that your constants will be high, so in practice your algorithm may not have very good performance, right? And that's a place where randomization comes in. You replace some complex logic by some very simple logic, and here is a way to do that with, in the case of closest pair, okay? So let's talk about how to do closest pair, and remember that for the most part, randomized algorithms are not, it's about forcing randomness and not about, completely a new way of solving a problem, right? So just like Quicksort, we already knew what it was. There was a problem with Quicksort that it was not predictable performance, and so we fixed that by doing randomness, right? So once again, in the case of closest pair, it's not the case that the core algorithm depends on randomness. The dependence on randomness is limited to expected performance, right? So runtime is going to depend upon the randomness, but the algorithm itself is not dependent on randomness, okay? So the way we are going to do this is, we are going to think about the problem in a different way, right? So we are going to create some sort of a hash table, right? The hash a single slot in the hash table will hold entries that are within a certain cell, right? So we are going to create a grid, and we are going to put points within the grid, and each grid cell is going to be one hash table element. Okay, so what is the reason why we want to do this? Because if I want to find the neighbors, then I have to look in my own table, my own cell, plus maybe the neighboring cells, right? So this way, my search for neighbors is going to be efficient, right? I just go index to my hash table cell, constant time expected. Again, the whole notion about constant expected time of hash table has to be re-examined, and we will do that in the next lecture. But for now, let's assume that we have a hash table that gives us order of 1 expected time. Okay. So then this approach basically limits the number of comparisons to a small number of cells, and if you can make sure that each cell has only constant number of elements, right, then we can say that each comparison step only takes constant amount of time. Okay, so what we are going to do is, the question is, what is the grid size, right? So it's not clear what is the grid size to use, right? Because you don't know what are the closest, how close the points are, right? The points could all be, in the square 1 by, x equal to 0 to x equal to 1 and y equal to 0 to y equal to 1, or they could be in the range of x equal to 0 to x equal to infinity, x equal to 100 and y equal to 0 to y equal to 100, right? So you don't know exactly, and it's not really a question of extremes, because there could be local pockets where there are lots of points, right? So you want to make sure that any cell contains a relatively small number of points. So you don't want to, you can't decide on the cell size ahead of time. So what we are going to do is, we are going to process these points one by one, right? And then we are going to keep track of the minimum distance we have seen so far, okay? And then our grid size is going to be a function of the minimum distance we have seen so far, right? Because once we know that the minimum distance is, let's say, 1, then we know that within a cell of size 1, there are only a small number of points. Okay, so that's why we want our grid to be proportional to the size of the closest distance.